want to go on with today's program now. It's a real thrill to have Professor Matthias Grosse Perdekamp here to tell us about the first 10 seconds of the universe. Matthias got his PhD from the University of California at Los Angeles. After that, he did research at Yale University and also Gutenberg University before he moved on to Brookhaven National Laboratory, which he's going to tell you about a little bit today, as a Riken Fellow. And we were thrilled to get Matthias to come here to the University of Illinois in 2002. And some of the research he's doing on the early history of the universe through very high energy collisions he's going to tell you about. He's a member of several experiments and does a lot of interesting work with an experiment that operates in Japan, the Bell experiment, and some other things with muons and things. He's got a very diverse program. He's got a lot of students that he works with. He's very well thought of, and we're real thrilled to have him come here and show us some cool demonstrations today. So without any further ado, please join me in welcoming Professor Matthias Grosse Perdekamp.
Thanks, Kevin, for the friendly introduction, and welcome to all. The question we are going to discuss today is a very old question. What is the structure of matter, and what is the origin of matter? We go back to the beginning of the universe because this is when the matter we have around us today was formed. So we have atoms like the hydrogen atom, which are made of nuclei and electrons, and in the nucleus there are protons and neutrons, which themselves consist of more fundamental particles, quarks and gluons. And the question my group asks is, how do those particles form the matter we see around us? And the answer to this question is found, or at least partially found, in the early universe. So on Long Island, close to Brookhaven, we are trying to come up with ways how to recreate conditions as they were present in the first few microseconds of the universe. So what we get today is a show which is not directly from Broadway. It's slightly off Broadway, and we open the curtain to our play. The cast are going to be the elementary particles. I mentioned some of them, quarks, gluons, electrons, muons, and we'd like to learn how do those form nuclear matter. How do they make protons and neutrons, which we observe in the world around us. The stage is our laboratory. And what I hope to show you in my talk, that a particle accelerator for heavy nuclei, which generates the highest energy densities we can have today in a large volume, how that can serve to go back to the beginning of time and investigate how matter was formed. So I will talk about the accelerator and then also the experiment which we use to carry out those investigations. And I will show you some early results which we have. So I said in my introduction that we are dealing with an old question. The question is about 2,500 years old. So humankind always has wondered what is the fundamental structure of matter. And for about 1,800 years, this was a question of philosophy. I should correct myself. For about 2,300 years, this was a question of philosophy. The first philosophers to raise this question were Leucippe and his student Democritus, some 400 years before Christ. They postulated that all matter is made from basic building blocks. So if we keep chopping down, if I would start chopping down pieces of the table, I will find, as you know, molecules, then atoms, then electrons and protons and neutrons. If I cut the protons and neutrons further, I find quarks and gluons. This is the so-called atomic hypothesis. The last 200 years of this business were quantitative. This is the area of modern science. And in the 1800s, chemists and also physicists came up with the first set of candidates for atoms. They found the chemical elements, hydrogen, helium, lithium, beryllium, etc., from which we can build the molecules we find in the world around us. In the early 20th century, it became clear that those are not fundamental particles, that they can be subdivided further. I have here a picture of the helium atom. Shown is the nucleus with 2 protons and 2 neutrons and 2 electrons orbiting the nucleus in the outer shell. I want to ask for some prominent help and quotation to illustrate that this is really a very fundamental question of science. This is a quote from Richard Feynman, which you'll find in his physics lectures. So he asks if there was some catastrophe, I guess, in which all scientific knowledge or all knowledge of human civilization was to be lost. And there was only one sentence we could pass on to whoever comes after us. What sentence would contain the most information? And his answer is the atomic hypothesis. The statement that all matter is made from atoms, small particles which cannot be divided into smaller particles, move around and interact with each other. So let's move to today's atoms. This is the period system of the 20th century. Great contributions to this period system are actually made here in Illinois at Fermi-Leschel Laboratory. Like Kevin Pitts, who just spoke to you, is a member of the team who discovered the top quark. Matter generally is made of fermions. We have 2 different classes of fermions, leptons and quarks. And we divide them up into families or generations. This here is the first generation, up quarks and down quarks, and then corresponding leptons are the electron and the electron neutrino. And for all practical purposes, if we look around us, this is what matter is made of. So up and down quarks are the building blocks of protons and neutrons, and the electron is in the shell of atoms. And neutrinos are very abundant, but it's difficult for us to see them. For example, the sun, with all its nuclear reactions, is a bright source of neutrinos. There are further generations, which we don't need to discuss now. However, I want to spend a little time on discussing force carriers. There is a second class of particles, which we call bosons. And those are the particles which transmit fundamental forces. We know 4 forces in nature: gravitation, the electromagnetic force, and then there are 2 nuclear forces. And whoever discovered them first was not very innovative with names. They are called the strong nuclear force and the weak nuclear force. And what these particles do is, in our modern picture of quantum field theory, they are the mechanism by which forces between elementary particles are mediated. An example is shown here. This is a cartoon of a hydrogen atom. The hydrogen atom consists out of a proton in the nucleus and an electron in the shell. In some simple picture, which is not quite correct, we have the electron orbiting the proton, and the force between the two actually comes about through the exchange of a force carrier particle of a photon, which is the force carrier particle for the strong interaction. Note, I give a dimension here. Atoms are pretty small, 10 to the minus 10 meters. But this is nothing for the tools we have today. We actually can study length scales down to about 10 to the minus 18 or 10 to the minus 19 meters. So 18 or 19 zeros before you hit the first one. And so it becomes possible for us to investigate the interior of the proton. And if you remember from the introduction, this is what we're interested in. We'd like to learn how in the early universe the proton was formed from up and down quarks and gluons. These up and down quarks are held together by the force carrier of the strong nuclear force, which are these gluons. So this might be an odd concept, that exchanging particles is actually somehow exerting a force onto elementary particles. But I think we can see in a simple model how this might work. Imagine yourself playing with two boats on a little lake, and you're actually playing ball with the partner in the opposing boat. And if you throw now a ball at your partner, this ball will carry some momentum and some energy to the partner and actually will push these two boats apart. So this is a good picture for a repulsive force. It becomes slightly more difficult for an attractive force, but you might imagine a boomerang which comes from the back. Those would push these two boats together. And this is the picture we have for interaction between elementary particles such as the proton and electron in a hydrogen atom, or such as quarks and gluons inside a proton or a neutron. So some of you might say, well, this is a fairly weird and remote reality. Remote in the sense that we are talking about the very microscopic, which is not accessible by our eyes. But in fact, in addition to elementary particles bound in matter, in our everyday life, we are surrounded by elementary particles all the time. I have one example here. There are more. This is the example of cosmic radiation. The cosmos is full of high energetic radioactive proton and helium rays, which are incident on Earth. And luckily for us, our atmosphere represents a very effective shield in protecting us from this cosmic rays. This cosmic rays, say a proton with very high energy, typically will make a nuclear reaction in altitudes of about 30 miles and generate a very strong shower. So the energy of the proton is transformed in many new particles. Most of them are unstable and make radioactive decays. There is, in fact, only one type of particle which can make it all the way down to the surface where we are, and those are muons. Remember where the muon is. Let me show you this quickly again. The muon is something like a heavy brother to the electron. It's the lepton of the second generation here. It is very similar to the electron, except that it has a larger mass by about a factor 200, and that it's unstable. It decays in about 2 microseconds. So I have listed here its properties. Now these muons we have on our surface, and roughly in this area here, which is maybe twice the area of my hand, we have one such muon per second. And the first demonstration I'd like to show you, and you have to be a little patient and watch it, is a so-called cloud chamber. This is the particle detector down here, and it's displayed up here on the screen. It has a saturated atmosphere of CO2 gas. And whenever a charged particle, a high energetic charged particle, moves through the cloud chamber, it will make a condensation trajectory. So what you're looking for here, for example, was a not very good one, is a fairly broad trace. They're going to be maybe of this length, and that will tell you that there was a muon. So if we turn our particle detectors on, we see these muons immediately. We don't need our particle accelerators to make high energetic particles. We have them around us at any time. And the mechanism, one of the mechanisms, there was a very nice one, there is a very nice one. The mechanism is explained here through cosmic radiation. So this is a member of the cast of our show, Regenerating the Early Universe in an Accelerator, which we have with us today. So now let's go to the play. The origin of matter, and that takes us back on a journey to the beginning of time, space, matter, and energy. we think that the universe was generated in a Big Bang at very high energies, and shortly after the Big Bang we had the elementary particles I introduced to you in our period system of modern atoms, and at some point in time these particles must have condensated into forms of matter as we have it around us today. So quarks, for example, and gluons have formed protons and neutrons. At some later time, protons and other nuclei captured electrons and formed atoms, hydrogen predominantly. So the topic of our research group and a large number of colleagues at Brookhaven National Lab is to understand how these basic building blocks, the blocks we think are the atoms of nature, how those make up the more complex structure we have around us today. First, protons and neutrons, which then themselves are building blocks for the nuclei, and those again are ingredients to the atoms. And then I think you are familiar with how one can build a more complex structure from atoms. So let's zoom in to the beginning. The time we actually try to generate, it doesn't make sense to us to go back to too early. This is actually Kevin's job. This is called high energy physics. If you're not happy with the kind of temperatures we can achieve in our accelerators, then you're a high energy physicist. The energies or temperatures we are interested in are pretty large. There's actually a broad range. I specify here 10 to the 13 degrees C. So this is a number with 13 zeros. And that's the temperature at perhaps about 5 microseconds after the Big Bang. And we are really interested in the time span from 1 to 10 microseconds after the Big Bang. This is the time where, I think this is a nice cartoon, where gluons and quarks start forming protons and neutrons. And there are also particles which consist of 2 quarks. Those are called mesons, but they are not very stable. They are not around anymore today. They are formed today, but the ones formed primordial are not there. But we are left with many of these protons and neutrons. This is the matter we have around us today. So we introduced the cast, the elementary particles. We introduced the play. And we have to make a decision where to go and see the show. And if you have been in New York or Long Island, you know that it's sort of neat to go out and see a play on Broadway. It's somewhat cooler to see a show off Broadway. You know, this is Manhattan with Broadway. Off Broadway is not very well defined. It's everything which is not on Broadway. So I make a circle here, which is Manhattan and Queens and Brooklyn. And if you really want to be hip, you go off Broadway. And this is where Brookhaven National Lab is located, and this is the show we're going to discuss today. There's so many neat things which come from high energy and nuclear physics. For example, the internet. This is something I pulled from the internet. It's Google Maps, and it allows us to zoom in from space onto Brookhaven National Laboratory. It's this entire site here. You can see the circle, which is the RIC accelerator. Brookhaven National Lab is about 60 years old. It was founded after World War II by the large research universities in the Northeast. This was about the time where research in high energy and nuclear physics became so expensive that it was not possible any longer to do this at a single university. And people got together to form national laboratories. Today, Brookhaven has about 3,000 employees, does research in a very broad area of topics, from high energy physics to brain imaging and brain research. And these national labs are really a great tool, I think, in our society to boost the progress in research. and the benefits to society are immense. Brookhaven, for example, is a leader in brain imaging, has identified the reason for cocaine addiction or has understood the mechanism in Parkinson disease, and there's very close interaction between high energy and nuclear physics and medical sciences on the other side. Like all the imaging, all the detectors typically come from the high energy or nuclear physics side. So it's a great place to work at. One can learn many things, not only directly in your own field. So now our problem is, how do we get back to 10 trillion degrees C in the laboratory? So how can we get back to temperatures or energy densities we had about 1 to 10 microseconds after the Big Bang? This seems to be a tough job. Let's look at an example which we can do in our own kitchen or our own lab here. We can boil water. This is a picture of boiling water at 100 degrees C. And this is familiar and perhaps not too exciting, but it allows us to very nicely see what we want to do. What happens as we warm up water from being a solid, ice, into a liquid, into a steam, is that we take existing structure of matter and sort of rip it apart and make transitions into new phases of matter. So we go from ice to liquid to gas. If we heat up further, we will actually ionize the atoms in this gas. We will deal with the plasma. And we want to continue this process until protons and neutrons themselves become unstable. And it really takes the 10 trillion degrees before a proton or a neutron will dissolve in the heat bath you put it into. That high energy densities are impressive. We can observe this on our own Earth around us. This is an example of what can happen at 1200 degrees C. Volcano eruptions are very impressive demonstrations of energy and natural forces. Very impressive one, which is not too far from us in the center of our planetary system, is the sun. We are at a modest 10 million degrees C in the core, so ways to go before we are at 10 trillion. This is 13 zeros. This is only 7. So we need 1 million times hotter than the core of the sun. This is a temperature which already leads to very exciting phenomena. We deal with complete plasma, and we have very active nuclear reactions, fusion reactions, which are actually the energy source for our daily life. This is the power source from which the sun draws its energy. So this is a cartoon of what we want to do, the trick we want to employ to generate this tremendously high temperatures. Let me first show you what this does on the matter side. So we start with some solid structure, and we warm this up. We will get free molecules. We heat this further up. The molecules will decay into atoms. We heat that further up. We will generate a total plasma. Electrons won't be bound anymore. If we go to even higher temperatures, the nuclei are not stable. Protons and neutrons are going to be released from them. And then finally, if we hit temperature densities as we had them at the early universe, we deal with free quarks and gluons. Yeah? This is what we have to do. In the universe, actually, we went this path. We started with the Big Bang and then had energy, quarks, gluons, etc., and then saw this condensation of matter. So how do we do this? The highest energy densities one can actually achieve can be achieved in particle accelerators. We let charged particles fall through very large voltage differences. And in order to get energy densities over a relatively large volume, we take the largest particles for which this can be done at the present time. They're not very impressively large, but compared to what Kevin does at Fermilab, this is pretty large. So we accelerate gold nuclei with a diameter of 14 fermi-meter, this is about 14 times the diameter of a proton, to a velocity which is 99.995% of the speed of light. So in addition to their mass, these particles will have very high kinetic energy. We then bring them to collision. You might wonder, why is it that I draw disks? This is actually a consequence of special relativity. If something travels at this kind of speed, its dimensions appear Lorentz contracted, so they change. So the spherical nuclei for us in the laboratory frame, if they are moving this fast, actually appear as disks. This actually helps us to increase the energy density as it compresses the density of matter even further. These two disks basically pass through each other. This is what's shown from here to there. And then what you're left with in between them is actually a medium which we believe is of the order of 10 to the 13 to 10 to the 14 degrees hot. And this is the volume in which we go back to the structure, energy density, etc. We had in the early universe. So that's all well, but I think there are two problems we need to address. The first one is, how do we accelerate nuclei to these very high energies? And the second is, how actually can we tell about this tiny volume at this high energy and what's going on in there? So before we discuss these two questions, I'd like to do a demonstration how collision of two particles can generate high energy densities. And our own accelerator here was closed down, I think, in the late 80s. So the only thing we can do, and it's a timely thing to do, is collide pumpkins, pseudo-particles. This one is a neutron, and this one here, it's still smiling, is a proton. Most protons don't know what's going to happen to them. I also should tell you, in a real experiment, you should not expect that things just work. So I think I could use some target assistance. Maybe John can help me. John is a graduate student who works on this experiment and will get his degree from studying proton structure and the formation of protons in the early universe. In an accelerator, we use the electromagnetic force to accelerate particles. Here we switch to gravity. And maybe in a personal note, I'm sort of disappointed by gravity. It's weak. You get much more bang for your buck if you use the electromagnetic force. But it's pretty good.
How high up do you have to go before gravity is no longer disappointing?
To the sun. What's this collision? Proton-neutron. John, could you stay there and tell me if I line up? I think you have to be over there. So this is what we do in accelerators, except that this stuff is about 10 to the 16 times smaller. And all right, watch. So please notice that if you generate a high energy density, you actually have the energy available to make new stuff, and it actually sort of comes out in all directions. Anyone who didn't see this? I have another one. All right, and it goes. Tough photon as targets. So this was the part of the lecture which took longest to prepare. It's actually thanks to Erica and Bernie who did this. So we went through this. Now we get to a real problem, how to accelerate particles, charged particles. And you may be aware that you all have particle accelerators in your home, or most of you at least do. You have TV sets. What we have in a TV set is a cathode ray. It's basically a ray of electrons which emerges from a heated filament back here. And then we have a system of deflection plates which use electric fields, but also coils which use magnetic fields to steer the electron beam across the TV. And we can demonstrate this. This is a cathode ray tube. It's historically a very interesting device. These are actually the type of experiments which gave us first access to knowing about elementary particles. The first one ever to be discovered was the electron in such a tube in 1895 by Thomson. And so we have the same here system of a filament which is hot and some deflection plates. And if I now come in with a magnet, you can see that I can steer this beam. Let me see, we have another demonstration to show. This is also an evacuated coil which has actually a little bit of a noble gas in it. And we may have to dim lights. I have to cover the actual setup, otherwise the light would interfere with seeing the electron beam. So this is an electron beam which is generated by a heated filament and then released into this gas. It excites the gas, and this is how we can see the beam. And what we can see here is how we can use magnetic fields to force this beam on a circular trajectory. This is basically what's going on in a real particle accelerator, in a collider at least. Here you can see two rings. This is at Brookhaven, one for positive gold ions and the other also for positive gold ions. And we actually inject them into this ring. And the first task we have to solve is we have to keep them on this circular orbit. And I think I just showed you that we can do this with magnetic fields. So for charged particle rays, magnetic fields are sort of like optics is for light rays. So we have a system of bending magnets who keep them on a circular orbit, and then also focusing magnets which make sure that the beam remains focused. And then in a second sort of hardware effort at an accelerator, it's necessary to accelerate them to very high energies. And this is done by so-called cavities. These are devices which can have very high electric fields. And it's actually inside these devices where these particles see very high fields up to about 10 million volts per meter. And since they go through this many million times, they keep falling through an increasing voltage potential and pick up energy. So this is what we have at Brookhaven, the relativistic heavy ion collider. Think of your TV set. If you ask, how does this work? This is something you probably should not do at home. It's bad for a color TV. This is a cathode ray tube. You will be amazed what in your personal life comes out of high energy nuclear physics. So a TV set definitely is one example. And something must be wrong with this channel. So you can deflect the electron beam. The electron beam scans quickly across the screen to build up the image. All right, now we have solved our first challenge. We are capable of colliding gold ions, and we generate this very hot volume, which unfortunately is very tiny. So how do we learn what's going on in this tiny spot? It's something we could not see with our eyes. So that's actually the next puzzle. How do we find out what's going on? And perhaps I show you another demonstration of what can happen if we have very high energy densities. This over here, and let me darken the room, is a bank of capacitors which can be charged to fairly high to fairly high energies or charge in the capacitor bank. And I then shorten it with a wire, which creates a very high current through the wire. Anyone who didn't see this? Oh. And the wire heats up. We have very high energy density in this volume. And what it does, it explodes. I have to discharge this. So if we create very high energy density in a small volume, we can generate stuff which comes out in all sorts of directions. We have seen this here. So the challenge is actually to somehow keep track of the stuff which is coming out and then try to reconstruct what must have happened in the first place in this small volume. This now is a more realistic scenario of what happens. These are the two Lorentz contracted by relativity gold disks which collide with each other and form this cylinder of very high energy density with quarks and gluons. And the quarks and gluons condensate into elementary particles which now are incident on whatever we device put there, a particle detector, and need to be studied in there. This is what we actually do see at Brookhaven. If we collide two very high energetic gold nuclei, this is a collision which is head-on. The two nuclei really line up perfectly. And this is a picture taken with the star detector. You might think of this detector as a camera which is capable of seeing the particles which come out of an event. And since we have these very high energy densities, we have enough energy to make a very large number of new particles. You all know Einstein's E is mc squared, so we have a lot of E, and that means we can make a lot of mass, lots of new particles. So in star, in a central collision, there typically is something like 2,000 particles generated. And the question now, I think I gave a good introduction. You maybe can answer, if you see these particles, how do you figure out what happened in this high energetic collision in this very hot initial spot? This seems to be impossible. And this is the actual challenge of this field it's called heavy ion physics. So we are dealing with this extremely complex, we call it a final state, of matter generated in this very high energetic collision. So we actually do this in 4 different places. This again is the lab, as I have introduced it to you. And shown are the 4 particle detectors, which we have in different collision points. Gold beams actually collide in 6 different locations, but only 4 are equipped with particle detectors. And I want to show you some detail about the Phoenix detector, one of them. This is actually the one John and I work on with a bunch of our colleagues here from the university. So perhaps we look at this schematic picture here. We have the 2 beams coming in. We call them, this is just a name, the yellow gold beam and the blue gold beam. And the collisions take place in the center of the apparatus. This is a very large apparatus. This dimension here is about 40 feet, and it's also about 40 feet high. I don't go into the details, but what we do is we surround this collision point with instrumentation. We call them particle detectors, which are capable of reconstructing these particle tracks, which you have seen in the previous picture. So this is basically the camera which can take a picture of the collision products. And once we have this picture, we can try to analyze it and try to understand what must have happened in the original collision. So Phoenix does very well in measuring electrons, muons, photons, hadrons, meaning protons, but also mesons and other unstable particles. It actually consists of 4 independent particle spectrometers which could be operated separately. There are 2, these 2, this one here and this one there, which specialize in the detection of muons. Remember, we were looking at the cloud chamber. So this very same particles which we see here from cosmic rays show up in abundant rates from heavy ion collisions in our muon detectors. So one thing I'd like to point out is that this is a very fast camera. There are about 300,000 different channels which are read out, and collisions occur with a rate of 10 megahertz, so 10 million times per second. And our detector, the technical term is dead time free. So we really can read out this 300,000 channels 10 million times a second. And we then have some fast buffers at the front end where the data rate is 5 terabytes per second. So that's a number of with 12 zeros. And it then goes to a computer system at the level of which the data flow has to be cut down to about 5 gigabytes per second. And from there, we write it to disk and to tape for analysis. But we still do this with a rate of 100 megabytes per second. This is a picture which shows you the 2 central parts of the detector. So it does not show the 2 muon arms, which are to the right and to the left. Here's a technician, which gives you an idea of the scale. And I thought I'd introduce you to one of the types of particle detectors we use. It's a so-called drift chamber. This is this piece back here. This is built by a collaboration between Russian colleagues from St. Petersburg, colleagues from Long Island at Stony Brook University, and colleagues from Florida at Florida State University. I'm telling you this to make the point that this kind of research is always collaborative. We have actually people from 60 institutions in Phoenix. And the way this typically works is that each group specializes on one of the technical tasks, one of the software tasks, and provides or helps to provide one of the detectors. So how does a drift chamber work? This is a simple example for a drift chamber, but it's actually a drift chamber which we just built for a local measurement here at Illinois. And John will be available after the talk to show you how this works. It actually consists of 2 plates which allow us to apply an electric field in this volume here. And the electric field is such that we have a positive electrode here, and a negative electrode there. Voltages are relatively high. This could be at about 2,000 volts. The whole thing is filled by a gas. In our case, it's an argon-based gas. And now what happens is, if a muon goes through, this is this yellow muon going through here, it ionizes the gas, so it kicks off electrons which are bound to the argon, indicated by the red dot here. I have one. It would typically generate in a centimeter something like 100 electrons. These electrons experience a force from the electric field and are pulled to the anode, the sense wire. And then at the sense wire, which is very thin, thinner than a hair, the electric fields strongly increase and accelerate electrons. They collide with argon atoms again, make many secondary electrons, and those then are collected by the sense wire, and this makes an electric pulse which is large enough to detect the particle. Yeah? And this we measure very precisely to about a nanosecond the time it takes for the electrons to drift from the muon trajectory to the wire. A nanosecond is the billionth part, so thousandths of a millionth of a second. And we then can calculate back, since we know the drift velocity, where this muon passed through, and we can measure the position of particle to about 0.2 millimeters or so. So the purpose of this detector here, it looks at the interaction point, is actually to tell us the trajectory of all these particles which are generated in the collision. There are other types of detectors which allow us to measure time very precisely. This here is an example for a scintillation detector. This is actually a device which, when a charged particle penetrates through, produces with a very fast time constant small flashes of light. And this light then is collected through these light guides into a detector. It's called a photomultiplier, which can amplify this signal. I'd like to demonstrate to you how light propagation works. So we have a light source, a laser, and let's shine the laser into a light guide. This might be the light guide which actually funnels the photons from the detector to the photomultiplier. And you see that the photons cannot escape the light guides and are eventually here led to the detecting device. This is a process which is extremely fast. We need to measure position, but we also have to measure time. With this kind of mechanism, we can measure time to about 0.1 of a billionth of a second. So that's the timing resolution one can get here. So this is another demonstration which shows you how light propagation works. It's a plexiglass cylinder, and I shine in my laser under an angle, and you see how the beam is trapped and travels down the cylinder in a helix. Now we have to go through this again. Oh, and this is the result. So we have this super fast camera, and this is the kind of picture it takes. And now you can imagine it takes 10 years to build this detector, and if we get a picture like this, we all stand in awe and watch it forever. Well, this is really true. This is actually our collaboration. I think I should say, as I show this to you, this is really the effort of very many. And we have 60 institutions from think now it's not quite up to date, 13 countries and 60 institutions and 520 participants. So the University of Illinois is one of many. And this is actually one thing which to myself is very appealing in this field. This is one of the main reasons, in addition to the scientific interest while I joined. An experiment like this is a fantastic place to meet people from all over the world, from Asia, from South America, from Europe, from Russia, often people from other political systems which otherwise we don't have access to. So you get first-hand information about stuff where otherwise you have to trust the media. And then on top of this, most of these people are pretty bright, and it's great fun to work and discuss physics with them. So this is, I think, a quarter of our collaboration gathered in front of a part of our detector, which is not fully assembled. This back here is one of these muon walls, which are 40 by 40 meters. And I guess I'd like to talk a little bit about the scale of the project. It needs a lot of people. There are very many channels which need to be instrumented. I mentioned already 300,000. Each of these channels needs to be amplified. The data needs to be converted into digital data and then collected and stored. I think this is a story, you can tell from my accent, I'm from Germany, which actually is from Friedrich Schiller, a writer in the late 1700s. And to my amusement, I discovered that this was picked up by Disney, but it's a very good picture. The data flow in Phoenix is never ending. I suggested that we stand in awe and admire these events, but in fact, we have no chance to do this. In a typical year, we take 500 terabyte of data. I think your typical hard drive at home may be 50 gigabytes. It can be larger. But we needed 10,000 such hard drives to store those data, which come in a year. And this corresponds to about 5 to 10 billion events, depending on what exactly we do. So the picture I just showed you, we actually have 5 billion such pictures. And we face a tremendous challenge to go through all these pictures and for each of them figure out what happened in this little collision. This amounts to a tremendous computing effort. So online, in order to handle this data transfer, we actually collect data with optical fibers. Each fiber, we use something which is called G-links, can transmit a gigabit per second. And we need 200 parallel fibers, which send the data to an online processor farm, which is 300 fast computers. And then from there, it's fanned out across the world. We have a very large farm at Brookhaven National Lab, and also a very large farm in Japan, and then smaller Phoenix computing centers in France at Oak Ridge National Lab in Tennessee, Vanderbilt University in Tennessee, and in New Mexico. Our group here works very closely with this institute at RIKEN. So this summer, most of us were actually in Tokyo to work on this computing farm for the analysis of the data we took earlier this year. So let me see, I think we have a demonstration. So at these high rates, it's convenient to use fiber optics for the data transfer. And one thing our group did this year, we actually got organized this data transfer from Brookhaven to Japan. And this is a fiber bundle, as we might use it at our detector. You can see, I have to switch the camera. This is the output observed with this camera here of this fiber bundle. And what you can see is that one can actually transmit information. So 270 terabytes of data to Japan through fibers. And this actually amounts to a world record, and it was picked up by our colleagues and competitors at CERN. we actually use technology they have developed for us. We didn't do the hard part of the work, but we actually organized it well. And we achieved data rates of 60 megabytes per second from actually Long Island to Tokyo, which made it possible to transfer the full 270 terabytes, so something like this 10,000 hard drives, to Japan in 2 months. So I want to conclude with some results we obtain. So we have now discussed much how we bring into collision gold ions to generate very high energy densities, and our detectors, which look at the reaction products to tell us what's going on. What's going on here is that we have a hot phase of matter with something like 10,000 gluons and quarks, we think. And I want to introduce you to one way how we actually can tell what's going on. So this gold nuclei pass through each other. Most protons and neutrons in the gold nuclei do not make a really high energetic interaction. But every once in a while, inside two nuclei, one coming from the left, one coming from the right, actually collide head-on. And if that happens, there's potential for completely stopping them. This generates very high energetic reactions, and we can make, as a result of this, very high energetic particles coming out. And now there's an interesting question. We sort of know what happens here if such a collision occurs if we are in vacuum, because we have measured it, for example, at the Tevatron or at CERN, etc. And we now ask the question, what happens to these very high energetic particles if they are inside this medium? We think that this is a medium which is as dense as the universe was a few microseconds after the Big Bang. It's a medium in which quarks and gluons are free, and the particles interact with a strong nuclear force, which is about a factor 100 stronger than the electromagnetic force. These are all things which we usually don't have. So perhaps there's a possibility that if these light-fast particles, which are extremely penetrating probes, go through this medium, it's so strongly interacting that they're stopped or greatly deaccelerated. And this is exactly what we see. This runs under the technical term of jet suppression. The stream of particles is called a jet, and we basically can make jets in which particles have almost speed of light inside our medium, and we can observe at which rate they actually occur, meaning at what rate do they come out of this medium. This is shown in this plot on the right side. This is the momentum, or the could be also the energy of these particles coming out. And this blue rate is basically the rate which you have in vacuum. Yeah? And then if you put this very high energetic, very penetrating probes into this medium, you actually stop 4 and 5 of these penetrating probes. And I'm not sure I can explain how amazing this is, but think of a safety window in a bank where people spend a lot of thought and technology to make it such that it cannot be penetrated by a projectile if bank robbery occurs. This projectile is not penetrating by our standards. This is much more penetrating. Any such window would be easily penetrated by any of the stuff which comes out here. It actually can penetrate a concrete wall which is several meters thick, at least some of them. This is very penetrating radiation. Now the amazing thing is, this is 14 times 10 to the minus 15 meters. So if you take your window in the bank, it's a billionth of a millionth of that thickness. And this medium here is capable of stopping this penetrating probe. This is why we say we have discovered a new form of matter. We don't work for the military, but if the military had this kind of shield, tanks would be very light. they basically had no walls. Of course, there's no technical possibility to do this. This is actually one of our discoveries which made it on the front page of Physical Review Letters, sort of the top journal you want your stuff to go in. And I have a little cartoon, which comes from my colleague Jeff Mitchell at Brookhaven National Lab, which tries to illustrate what's going on. So this is the point where these two quarks reacted, and please watch the jet of hadrons coming out to the top and the bottom. This is in vacuum, and this now here is in the hot dense nuclear matter, which was formed into in a gold-gold collision. So now we start. So in vacuum, you see that both sides make a transition into these jets of penetrating particles, where here much of it which goes into the dense medium is absorbed, and only the stuff which actually aims to the outer boundary can make it out. So this is the one result I wanted to show you, and I want to summarize by saying that this took about 12 years. We built a tool to study the formation and structure of nuclear matter as it must have happened in the early universe. And I think these are exciting times. Humankind has tried for 2,400 years to understand this. The brightest minds in philosophy and then for 2 centuries in the sciences have tried to understand this. And we live at the time where we will solve this puzzle. We will solve it at Brookhaven, we will solve it at Fermilab, at Jefferson Lab in Virginia. There are also some places abroad, in Japan and Tsukuba, in Europe, in Hamburg, Daisy, and Geneva. But this is really of historic dimensions. In another 2,500 years from today, people might not know what my country was. It probably is forgotten, but they will remember these results. So thanks for your attention.